So looking at some typical examples here, we have the metal sodium, which as an atom has 11 protons, being atomic number 11, and 11 electrons, so it's electrically neutral as an atom, as it's listed in the periodic table. In reactions, sodium will often lose one electron. And losing one electron means that it has 11 protons like it did at the beginning, because it's not gaining or losing protons. They're hidden way down in the nucleus. They don't change, but it now has 10 electrons. That makes it a cation with a plus one charge. It's plus one because it has 11 positive charges and only 10 negative charges. So there's a positive charge left out that isn't being canceled out. You can write this reaction or this process as Na, which represents just an atom of neutrally charged sodium, going to Na plus, which is how you write the formula for an ion with a plus one charge. It's just the symbol for the element with a plus as a superscript after it, plus one electron. So when an atom or a molecule loses something during a chemical reaction, rather than writing that element or molecule minus whatever it's losing on the reactant side, we tend to write what it's lost as a product. So that is, one sodium atom is equivalent to a sodium plus one ion plus one electron. This also introduces a concept that will be important in the future, and that is, notice that there is a balance of the charges from one side of this equation to another. Na as an atom, as the neutral element, is obviously neutral. On the product side, we have a positive charge and a negative charge, which when you combine them is neutral. So there's zero charge on the left side, zero charge total on the right side. That's what we call charge balance, and it is something that we'll have to keep an eye on as we're writing reactions in the future. So the ion charge depends on the relative numbers of protons and electrons. If the number of protons is greater than the number of electrons, it's going to be a cation, positively charged ion, and the charge will be plus one for each proton that's not being canceled out by an electron. If the number of electrons is greater, then what you'll have will be an anion, or a negatively charged ion, and the charge will be minus one for each excess electron. Okay? Also, we could look at a typical non-metal. Like chlorine. Chlorine has 17 protons and 17 electrons as a neutral atom because it's atomic number 17. And so since it has 17 positive charges and 17 negative charges, it's neutral overall. In reactions, chlorine usually gains one electron. Which leaves you with 17 protons and 18 electrons. And that means that it will be an anion. since it has more electrons than protons, and the charge will be -1 because it got one more electron than it has protons. In terms of a chemical equation, you can look at it like Cl, that represents an atom of the neutral substance, plus 1 electron leads you to the ion Cl-, which is known as the chloride ion. Interestingly enough, negative ions get special names, whereas positive ions are just the name of the element. So an Na+ ion is just called a sodium ion, but Cl- is called a chloride ion, not a chlorine ion. Notice that the charge does balance here. You got a total charge of -1 on the left and a total charge of -1 on the right. So everything works out and everything is happy. Turns out that ions are actually more common in nature than neutral atoms are for most elements, at least for the more reactive elements. You'll have some of the less reactive elements like, say, gold and silver and copper that you'll often find in the form of the actual element in the rocks. You know, you can go panning for gold and you can just find little bits of gold sitting at the bottom of streams and rivers as gold, and it's still even shiny because gold is not very reactive. Most elements are fairly reactive, and that means that most of them react to form compounds containing those elements at some point before we actually find them. And so something like sodium or chlorine, you will not find those in their elemental form in nature. You'll find them as part of compounds, like, for instance, sodium chloride. Also, ions have properties that are quite different from the compounds that contain them. Just like atoms do. When you take, say, hydrogen atoms and combine them with oxygen atoms to form water, you end up with a compound that has very different properties. Hydrogen is an explosive gas, and oxygen is a gas that really promotes combustion. And when you put them together, you get a liquid that puts out fires. So that's quite a difference just because you've bonded things together. Well, the same is true for ions. You know, sodium and chlorine combine to form sodium chloride. Sodium, the element, is an extremely reactive metal. It reacts violently with water. Chlorine is an extremely reactive gas. It will instantly corrode just about anything around it, and if you breathe it, you're going to have real problems. But you put the two together and you get sodium chloride, which is something that, at least in small quantities, we actually need to survive. Okay, and also, it's important to remember that any compound containing ions have to have an equal total positive and negative charges. Because the goal is to make a compound that's neutral overall. Like, for instance, sodium chloride. Sodium ions have a +1 charge, chloride ions have a -1 charge, so they go together in a 1-to-1 ratio to form NaCl, which has no charge overall, even though the individual ions do. All right, next we want to go on to the next section, which is about the periodic law and the periodic table. The periodic table is something that I'm sure everybody has heard of. It's sort of the, I don't know, sort of the centerpiece of any chemistry lab or classroom probably. And it's an extremely important tool for use in chemistry. And the periodic law is what actually led to the development of the periodic table. Because the periodic table is important to us not just because it's a list of the known chemical elements and some of their more important properties like atomic number and atomic mass, but also you can tell a great deal about an element, a great deal about its properties and behavior from where it is in the periodic table. So it turns out the arrangement of the periodic table itself has a lot to do with what the elements are like. The periodic table was first developed by a Russian chemist by the name of Mendeleev. And in 1869, so just over 150 years ago, he noticed certain repetitions in properties. And what he did was he took and arranged the known elements at the time, which there's only about 65 of the elements that we know today. And he arranged them in order of increasing mass. In other words, when you took the known elements and arranged them in increasing mass, starting with the lightest and ending with the heaviest, he noticed that the properties would change in a predictable way as you went from one element to the next. And they would change in predictable ways for a little while. And then when you went to the next element, they'd sort of go back to the beginning of that pattern and repeat all over again. The properties didn't repeat exactly, but they repeated at least qualitatively, so that elements at certain intervals within that list had properties that were at least similar to elements a certain distance away in the list. And this is what became known as the periodic law. It's that when elements are arranged, NTS, arranged and in order of increasing mass, certain sets of properties repeat periodically. So hence periodic law. Mendeleev arranged the elements in a table with the elements in rows where the masses increased left to right. Okay, and these rows are what we now know as periods in the periodic table. And it ended up with elements with similar properties ended up in the same vertical columns. Okay, and the columns are now known as groups. Today, whoops. There were some gaps in Mendeleev's table. And because of the way the properties of the elements varied predictably from one space to the next, Mendeleev was actually able to predict the properties of the elements that would eventually be discovered to fill in those gaps. And this is one of the signs that a theory or a law in chemistry is really onto something, that is really valid, is the more future developments that are able to be predicted using the tenets of your theory or law, the more firm and the better the law is. Okay? So that fact that he was able to predict that not only would these elements be discovered someday, but he was able to predict with great accuracy what their properties would be, that was a big deal. There were also a couple of anomalies in Mendeleev's table, where when you arrange the elements by atomic masses, the properties in a couple of spots don't vary quite in the way that you would expect. There are a couple places where the properties actually are kind of like, they vary but backwards from what you would expect them to do going one space to the next. And that's because the properties actually vary according to atomic number, which is the way modern periodic tables are arranged. And it was found, Mendeleev, to sort of in his defense, Mendeleev did not know about protons, and nobody in his time knew anything about atomic number. And so atomic mass was really the best gauge he had for comparing the elements to each other. Once atomic number was discovered, it was found that there are a couple of places where the atomic number and the atomic mass don't both go up at the same time. The atomic number goes up from one element to the next, but the atomic mass goes down. And when you rearrange the periodic table according to an atomic number, a vast majority of the elements remain exactly where they were, but there are a couple spots in which two successive elements actually switch places. And that had the effect of taking care of the anomalies in Mendeleev's table. So now the properties do vary the way that you would expect them to in those instances. And so modern periodic tables are arranged according to atomic number. And of course, the modern table also includes elements that were discovered since 1869. There is an interesting illustration in the text on page 59 where they show the periodic table and they color in the elements according to when they were discovered. And Mendeleev was basically dealing with the elements that are this color. And you can look at the diagram because the colors aren't coming through very clearly on the video. Basically, he had the elements that are shown in this color, and some of the ones that are shown in this color, but none of these and none of these. And so he was at a real disadvantage, and he still managed to do some really impressive work. Okay, so to have a look at the elements in the periodic table, there are several different ways to classify them. One of the most common ways, let's start new on this because it's kind of separate. Okay, there's several ways to classify elements. One of them is according to metals or nonmetals. Metals, the divisions between metals and nonmetals and stuff in between is shown on page 60 in the textbook in different colors, which probably don't come through very well on the video. But anyway, if you notice the dark zigzag stair step thing that goes down the right-hand side, that's basically the division between metals and nonmetals. Everything to the left of that would be metals except for hydrogen. Hydrogen ends up where it is because of its electronic structure and the kinds of compounds it forms, even though it's actually not a metal. But everything else over here in this entire part of the periodic table, which is obviously a vast majority of the elements, is a metal. And actually everything in those two rows way down at the bottom there, the lanthanides, I can't show it, the lanthanides and the actinides down there, those are metals also. So like I said, that's something like 90 elements out of the entire periodic table that only has, it had 116 when this book was published, but I think it's up to about 118 now. The nonmetals are the elements in green on this table, and those would be the elements in the upper right-hand corner of the periodic table. So you can see there really aren't very many nonmetals among the elements. But as it turns out, we'll see a little bit later, nonmetals are really, really versatile. They can do a lot of, you can do a lot even with the same two nonmetal elements. They can combine in a lot of different ways. Anyway, so metals, they are on the basically the left and the center of the periodic table. And some of their properties. Well, okay, that's, this needs to go. As I mentioned, vast majority of elements are metals. And something that metals have in common is that all of them are solids at room temperature, except mercury, which is a liquid. Some of the metals are actually relatively soft. We tend to think of metals as things that are hard because the metals we're most familiar with are ones like iron and copper and things like that, which are pretty hard. But those are actually the less reactive metals. The more reactive metals, like sodium, are things that we don't handle very often because they react violently with water. But actually, it turns out the sodium and metals like it are actually pretty soft. They are solids, but you can cut them with a knife. And that's something that you can't do with the more familiar metals. In a metal, the atoms are generally strongly attracted to each other. But they're not fixed in place. So in other words, this is why when you take a piece of metal and hit it hard with a hammer, it tends to squash out instead of just shattering and breaking into a million pieces. And that is what's known as being malleable. Malleia is just the Latin word for hammer, and, or sorry, malleus is the Latin word for hammer. And from that, we get the word malleable, which means that it can be formed into a flat sheet by hammering. Now, there are a lot of the nonmetal elements can be formed into a flat sheet by, say, dissolving them in a solvent and then letting it, lay out in a thin layer and letting the solvent evaporate. But you can't get them that way by hammering them. If you take another element like, say, carbon, a common form of carbon would be graphite, like the graphite in pencils. Take a piece of graphite and try hitting it with a hammer and see what happens. It does not squash out. It shatters into a million pieces. And that's true for basically all of the non-metal solids. So, but with a metal, you can hammer it flat into a sheet. Now, some metals are harder to do that with than others. Something like lead is fairly easy to hammer into a flat sheet because it's relatively soft, and something like steel is much harder to do that with, but you can do it. And also metals to some extent are ductile, meaning that you can form them into a wire-like shape by drawing them out through a small hole and like a big heavy piece of metal, which is called a die. And so by pulling the metal out, you can actually pull it into almost like a thread or a wire. Now, other elements can be formed, non-metal elements can be formed into wire-like shapes, like, for instance, pencil lead, which as I said before, is carbon, which is a non-metal. It looks, if you take the lead out of the pencil, it looks kind of like a wire, but they don't get it into a wire-like shape by drawing it out through a die. And that's the important difference. Non-metal solids are much too brittle to do this with. Also, metals tend to have a weak hold on their atoms. So when metals are reacted with nonmetals, metals almost always end up losing electrons to the nonmetals. And the metal becomes a cation, or a positive ion. And they're also good conductors of electricity for that reason, too. Metals can be thought of as a three-dimensional arrangement of fixed nuclei, but with electrons that can move very freely around the nuclei. And that's really how metals conduct electricity. It's those electrons moving around the nuclei. Because they are fairly dense and their particles are close together, metals tend to be good conductors of heat also. Heat energy has the effect of causing atoms within a substance to vibrate, in place, as we've mentioned before. That's the effect of thermal energy. And temperature is just a measurement of the average kinetic energy of the molecules, involved in that vibration. And in order for heat to travel through a substance, it requires, generally for it to travel quickly and efficiently, it requires fairly close contact between the molecules so that the vibration of one molecule can be efficiently transferred to the molecules next to it, and so on and so on and so on, all through the substance. And so substances with particles that are pretty close together, like metals, they tend to be good conductors of heat. Metals also tend to be shiny when they're clean anyway. They can, they can tarnish, most of them. Gold really doesn't tarnish, but most of them can. And so some examples of metal would include sodium and calcium, which a lot of people don't even realize are metals, but they are. And then some of the well-known ones like copper, iron, gold, silver, lead, and a lot of others, as you can see from the periodic table. So as if metals is the first category, you can probably guess the next will likely be nonmetals. Nonmetals are in the upper right of the periodic table. and they're a small minority among the elements. Their properties. For one thing, the properties of nonmetals vary quite a bit more than the properties of metals. For one thing, for example, for the metals, just about all metals are some shade of gray, except for the obvious ones like gold and copper, which are gold and copper colored. The nonmetals have a wide variety of different colors. Sulfur is yellow, phosphorus can be either red or white. A carbon tends to be black unless it's diamond, then it's colorless. Bromine is purple, iodine is, sorry, the other way around. Bromine is reddish brown, iodine is purple, and so on. So yeah, there's quite a bit of variety. And also, nonmetals can be solid, liquid, or gas at room temperature. And they're not malleable or ductile. And that's because the solids are brittle, like I mentioned about graphite, very brittle. They're generally poor conductors of heat and electricity. They can be shiny, but not all of them are, because obviously some of them are gases, and it's hard for a gas to be shiny. But some of the solids can be shiny. Even graphite is actually kind of shiny. Diamonds are very shiny. And again, when reacted with metals, the nonmetal will gain electrons. And become an anion. Some examples of nonmetals would be things like hydrogen, carbon, sulfur, neon. These are all nonmetals. Okay, I think that's probably enough for this segment. I'll end this and we'll come back with the last one right after this.